bit. And so I'm going to cover the following topics. Obviously, PFAS is perfluoroalkyl substances, also stands for polyfluoroalkyl substances. And I'm going to talk about the following topics this afternoon: chemistry, sort of basic chemistry, PFAS. You didn't think you'd get away without having some sort of a chemistry lesson this afternoon. So we're going to talk about some basic chemistry and some PFAS chemistry. We're going to talk about properties of PFAS chemicals, a little bit about the history of PFAS, some industrial applications, and how PFAS is released into the environment. We're also going to talk a little bit about treatment technologies, and then we're going to sort of end the discussion with regulatory discussion about the regulatory environment. So I'm just trying to bring up the chat box.
It should be in the More section over there with the 3 little dots on your screen.
Yeah, I'm sorry, I'm not seeing it.
Steve, we'll moderate the chat for you and the quick Q&A as we go. So at the end of your presentation, we'll moderate that for you, since it's
okay. So let's start with the chemistry. As you can see here, I've brought my own virtual drawing board to have a little bit of a chemistry lesson. So what I'd like to do is do sort of a basic chemistry discussion. So let's start with this element. And Jillian, what I was hoping for was that somebody could chat at me and tell me what element this is, just to see if the chat's working.
Carbon.
Very good. So this is working. So we're going to proceed. So this is the fundamental building block of organic chemistry, obviously. And yes, we got that right. It is carbon. Hang on for 1 second.
I'm sorry, I meant chocolate.
Very good, Jack. Okay, I've got the I got my chat box open. So okay, so yeah, Corona? That's correct. I'm sorry?
Didn't you mean Corona?
Yeah, not Corona, definitely carbon. So so a little bit about carbon. Carbon has a maximum of 4 bonds associated with it in organic chemistry. So I've represented that here with these 4 bonds. And now I'm going to bond it with another element. These are hydrogens, okay? So you can see this compound that I've created here, which is CH4. And I was hoping that somebody could tell me what that chemical is. You can either chat it at me or, because I've got my chat window open, so you can either chat it at me or.
Is that methane?
It is methane. Very good. Now, if you would chat that at me, I could have seen who said that. But yep, it is methane. Okay, so this is a fundamental compound, organic compound, CH4. It's methane. It's also a greenhouse gas. So that was very good as an exercise. Let's try another one. Here are two carbons and their bonds, okay? And I'm going to bond this chemical also to hydrogen. And that is C2. You can see 2 carbons and 6 hydrogens. So C2H6. And can someone tell me what that chemical is? This is just to see if everybody's awake. Now, if you were chatting at me, I could see who's paying attention.
Ethane.
So, I'm sorry?
Ethane.
Ethane. So that's right. So we've got methane and ethane. So 1 carbon and 2 carbons, methane and ethane. So that's true. This is ethane. So again, another building block in organic chemistry. So we could continue this on. We can build carbon chains using carbons and hydrogens. So you can see here that I've got a 3 carbon chain with all of its hydrogens attached to it. That is propane. I've got a 4 carbon chain. So there's 4 carbons here with all of its hydrogens. That's butane. And I've got 5 carbons with all of its hydrogens. That's pentane, like a pentagram for 5, so 5 carbon chain. And hexane, which is a 6 carbon chain. Heptane, which is a 7 carbon chain. This one you should be familiar with. This is octane. It has 8 carbons and it's got all of its hydrogens. So there's 8 carbons and 18 hydrogens. So 2 times 8 plus 2, that's 18 hydrogens. This is nonane, which is 9 carbons and all of its hydrogens. And this is decane, which is 10 carbons and all of its hydrogen. So these are like fundamental building blocks of hydrocarbon chains. Propane, butane, pentane, hexane, heptane, octane, nonane, and decane. And the reason that I bring this up and present this to you is because these carbon chains, they represent alkyl functional groups. So carbon chains, both long and short carbon chains. So you can see propane here, which is a short 3-chain carbon, and decane, which is a 10 carbon long chain. These are alkyl groups. Okay, so alkyl in this context means long carbon chains. So that's something to recall. So let's relate this to PFAS chemistry. Okay, so here we've got a 4 carbon chain. Okay, which based on what the previous slide, 4 carbons is which of those long chain or short chain carbons? Can someone tell me? Oh, Daniel got it right. Daniel gets a shout out for coming up with butane. So that's right. So here's a 4 carbon chain. It's butane based. Here are its bonds, its chemical bonds. And this time I'm going to replace those hydrogens with fluorine. Okay. So I've created a compound with 4 carbon chains and 10 fluorines. Okay, C4F10. Okay, so can anyone take a shot at what the name of this compound might be? There's 10 fluorines and 4 carbons. So we know one thing, the carbon chain base is butane. So anyone venture a guess? Checking the chat. 10 fluorines, anyone? Okay, seeing none, so I'll give you the answer. This is 10 fluorines, okay? So 10 fluorines is deca for 10, like a decade. So this compound is decafluorobutane, okay? 10 fluorines and 4 carbon chain, decafluorobutane, C4F10, okay? Everybody following me? I'll assume that you're all shaking your heads yes. Any questions at this point? So decafluorobutane. So let's take a look at another compound. Okay, this compound has 1, 2, 3, 4, 5, 6, 7, 8 carbons and all of its fluorines. So it's 16 plus 2 is 18. So this is a 8 carbon chain, which we know is
Octane.
octane. Okay, so we've got an 8 carbon chain for octane and all of its fluorines. Okay, and I'll give you the name of the compound. It's octadecafluorooctane. Okay, so octane for 8 chains and octadeca means 18 fluorines. So octadecafluorooctane. Okay, pretty long name, a little bit of a tongue twister. It also goes by the name of perfluorooctane. So if you could sort of see where we're going here as we're building up our understanding of PFAS chemistry, per in this context in chemistry is the prefix and it stands for the word fully. So perfluorooctane is a fully fluoridated carbon chain. Okay, so per meaning fully. So fully fluoridated octane chain. Okay, everybody following me so far?
Okay.
So let's take a look at another compound. Okay, this compound also has 8 carbons, 1, 2, 3, 4, 5, 6, 7, 8. So it's an octane-based chemical.
It's a
It
fluoride.
has, I'm sorry, is there a question? Sorry. So 8 carbons is octane. Now out here on the end, you can see that I've added a new element to the compound. This is a carboxylic acid group, C double bond O OH. This is referred to as the head. So I've added this carboxylic acid to this long chain hydrocarbon, okay? And it has, like I said, 8 carbons and fully fluorinated. This compound is perfluoro, which means it's fully fluorinated, okay? Every bond is a fluorine. Octanoic acid, okay? So perfluorooctanoic acid, which you should all recognize as we've been, looking at PFAS chemistry for quite some time. This compound is referred to as PFOA, which is a very common perfluoro compound, which is widely discussed. And we'll be talking quite a bit more about PFOA as we go along. So what we have is, in terms of PFAS chemistry, we have a perfluoroalkyl substance, PFAS. It means it's fully fluoridated alkyl long chain carbon substance. And this one happens to have a carboxylic acid group. We've just talked about it, PFOA. Okay, this is how these compounds are named. So here are a couple of others that you should be familiar with if you've been following along on the sort of the PFAS adventure here. These 3 fall into the category of long chain PFAS chemicals. They have, you've just seen PFOA, perfluorooctanoic acid. This should be the other one that's familiar to you, which is PFOS abbreviated. It's perfluorooctane sulfonic acid. You can see the difference between this chemical and this chemical is this has a sulfonic acid head and this is the tail they refer to as the long chain alkyl chemistry. This is PFNA, which is perfluoronanoic acid, which has 9 carbon chains. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9. It also has a carboxylic acid head to it and is referred to again as perfluoronanoic acid. And you should be familiar with its abbreviation PFNA. Okay, I hope everyone's following me. So those were 3 long chain PFAS chemicals. This is an example of a chemical that you should also be familiar with and should have seen. This is a short chain PFAS chemical. It's perfluorobutane sulfonic acid. Okay, it's butane. It's got 4 carbons, 1, 2, 3, 4. It's fully fluoridated. It has all of its bonds are fluorine, and it has a sulfonic acid head to it. Short chain, only 4 carbons, PFBS, okay, perfluorobutane sulfonic acid. You notice here that I referred to it as a replacement chemical. These short chain PFAS chemicals have been introduced as short chain replacements to the longer chain PFOA, PFOS chemicals, which we'll talk a little bit about here in a minute. But this is a short chain replacement for the long chain hydrocarbons. Short chain are considered to be, I guess, less toxic. They've been introduced, they were introduced recently as replacement chemicals for the long chain hydrocarbons. This chemical right here is hexafluoropropylene oxide dimer acid, which is abbreviated as HFPO-DA. You may have heard of this chemical referred to in the PFAS chemistry world as Gen X. This is one of the Gen X compounds. It is also a replacement chemical for some of the longer chain PFAS chemicals that were introduced early on. You'll notice that this particular chemical is not fully fluoridated by virtue of this oxygen right here. Because it's not fully fluoridated, it is not a perfluoro. This is a polyfluoro PFAS chemical because it is not fully fluoridated. But generically speaking, it's referred to as a Gen X compound. Okay, and we'll talk a little bit about that in a bit. So that was my quick little introduction to PFAS chemistry. If you've got any questions, you can just throw them up there on the chat. Otherwise, we will proceed. So let's talk a little bit about PFAS and their properties. So here's the PFOA we just talked about. Let's talk about some of the very most important properties of PFAS chemistry and PFAS compounds. PFAS compounds are mostly solid at room temperature. They're either powdery or waxy. I like to think of them, in terms of the word waxy. It sort of implies a lot about their properties. They have sort of a waxy feel to them. Another important property of PFAS chemistry is that the carbon-fluorine bond is extremely strong, okay? And this is one of the most important properties. So, so Chris just came up with a question. He says, are these forever because they are fully linked to each other, no loose ends or other compounds to latch onto? So good observation. Because the carbon-fluorine bond is so strong, and you can see here this PFOA has a fully fluoridated chemical. These bonds, the fluorine-carbon bonds, are so strong, practically unbreakable, which is why people do refer to them as forever chemicals. Also, you could see and sort of picture this, the compound is very dense, okay? The fluorine carbon interaction provides what they call steric hindrance, which makes other compounds very difficult for other compounds to interact with PFAS chemicals, which is one of its most important properties. So extremely strong bonds, very difficult to break, very difficult to react with for the most part. And that is one of the reasons why they refer to them as forever chemicals. They've got some very interesting properties, one of which is that PFAS chemicals are referred to as lipophobic, which means that they do not interact with oil. They actually repel oils and fats. As you can imagine, if you can see just based on this chemistry, they're very tightly packed, very hard to get at, very strong bonds, which means that this chemical repels things like oils. It is also has another interesting property, which is why it's been so widely used. PFAS chemicals are also hydrophobic, which means that they repel water. So it's an interesting chemistry. It both repels oil and water. And again, it is based on the fact that these are very strong bonds and they're very densely packed in. They're very unreactive, at least the tail section of the compound, very difficult to react with. The other property that's important is that they're very thermally stable. So they're very hard to break up, again, based on their chemistry. They're very thermally stable, and they do a fantastic job of reducing friction. Okay, so again, they're waxy, slippery. They do a very good job of reducing friction. So these are probably the most important and key properties of PFAS chemicals. And again, they're based on this sort of dense chemistry that you see here. Okay, so let's move on to history. If there are, I don't see any questions in the chat about the properties other than Chris's. So let's move on to history. So PFAS chemicals were initially introduced in the 1930s. They went through their initial development. In the 1940s, the first PFAS were introduced, the two that we have spoken of previously, and you most commonly hear referred to as PFOS and PFOA. They were initially produced. They were used for non-stick coatings. Those were introduced in the 40s. Now, can someone sort of chat at me the sort of trade name for non-stick coatings that PFAS brought about?
Teflon?
Yep, Teflon. So Teflon's the right answer for non-stick coatings. In the 50s, PFAS was also used for stain and water resistant products. You had heard, previously that one of the properties that, or two of the properties that they are both oil and water repellent. So in the 50s, they were used considerably for stain and water resistance. And Jack West answered this question in advance. Thank you, Jack. But when it comes to stain and water resistant products, can you think of a name of a trade name that was used for those products? And Jack has already provided the answer, which is Scotchgard. So if you can imagine, everything manufactured, upholstery, furniture, and so forth, carpeting, they were all Scotchgarded. And Scotchgarding is a sort of a classic PFAS chemical. So PFOA was also in the 50s used for protective coatings. In the 1960s, PFOS was introduced as a firefighting foam. You hear a lot about this, and we'll talk a little bit more about this as we move on. But in the 60s, it was used for firefighting foams, and PFOA was also introduced for protective coatings. In the 1970s, PFNA, which is the 9 carbon chain compound that we had looked at earlier, was introduced for architectural resins. They also introduced poly PFAS chemicals. These are referred to as fluorotelomers. They were introduced for firefighting foams. And in the 70s, actually it was in the late 1960s, this product was introduced, but a Teflon-based waterproof fabric was introduced. Now, can anyone give me the trade name for a Teflon-based waterproof fabric? Everybody had them on the golf course. Anybody have any idea? You may have been familiar with. Yep, Daniel got it. Gore-Tex. Very good, Daniel. So a Teflon-based fabric that was introduced in the 70s, Gore-Tex is a trade name. You also see here that in the 1970s was the first indication that PFAS substances were accumulating in the body of exposed workers. So this was the first sort of instance and study that PFAS chemicals were, again, getting into the body and accumulating. This happened in the 1970s. Throughout the 80s and the 90s, PFAS had continued use. In fact, they introduced many PFAS chemicals. Anybody want to take a guess at how many PFAS chemicals were introduced, just sort of in round numbers? No takers on that question? So it's been said that there are over 6,000 different PFAS chemicals right now that have been introduced. So it's certainly not in the hundreds, it's in the thousands of variants of PFAS chemistry, both short chain replacements, Gen X chemicals, and also long chain PFAS chemicals. In the 2000s, as I had mentioned earlier, they started replacing long chain PFAS chemicals with short chain PFAS chemicals like PFBS. And they also introduced Gen X replacements like the compound that we had mentioned earlier, the HFPO-DA. And also in the 2000s, the US, recognizing the fact that PFAS chemicals were accumulating in the bodies of exposed workers, they started to reduce the amount of long chain PFAS chemicals that were available in manufacturing. Manufacturers also voluntarily started reducing the amount of manufacturing of these long chain PFAS chemicals. So that's just a quick little history lesson. Obviously, there's a lot more to it, but should give you some idea of sort of the evolution of PFAS over a period of time. So I mentioned earlier that PFBS, which is perfluorobutane sulfonic acid, was a replacement chemical for PFOS, which was a chemical that was voluntarily phased out by US manufacturers. It was offered as a short chain replacement. PFBS, however, has also been identified in the environment and consumer products, including surface water, wastewater, drinking water, dust, carpeting, and carpet cleaners, floor waxes, and food packaging. So they introduced this short chain replacement for the long chain PFAS, but they are also finding this chemical in widely in the environment. as is the same is true for Gen-X chemicals. So Gen-X, which is really a trade name for a technology that's used to manufacture these fluoropolymers, they were also introduced as replacements for long chain PFAS chemicals, but they have also been found in surface water, groundwater, finished drinking water, and so forth, rainwater, and also in some air emissions. So even though they were offered as replacements, they are still found in the environment. So any questions about that brief history? If not, I will move on to industrial applications, give you some idea of where these chemicals have been used historically. So because of the properties of PFAS, both being able to repel oils and fats and also able to repel water, they have been widely used in a number of different industries, some of which we have already mentioned. Almost any industry that you can think of uses some of these chemicals, like aviation and aerospace. They're widely used in the automotive industry in terms of surface treatments for upholstery and carpeting. I'm not sure if they're responsible for the new car smell that everyone talks about, but I feel that they probably are. They're used, again, to treat upholsteries and carpeting in the automotive industry. They're used in biocides like herbicides and pesticides. They're widely used in building and construction, as you can imagine, in paints and coatings and surface treatments. They're used in the cable and wiring industry for coating and jacketing. So if you have ever tried to pull wire through conduit, for instance, bundles of wire pulled through conduit, you could appreciate why jacketing using these chemicals with their unique properties of either waxiness or slipperiness make them ideal for this sort of application. They're widely used in cosmetics and personal care products in terms of shampoos, nail polish, eye makeup, dental floss. Everyone can sort of picture the waxiness of dental floss. They're used in electronics. They're used in the energy industry. They're widely used in firefighting and safety, both in terms of equipment and clothing. You hear mostly about PFAS chemicals for firefighting in terms of firefighting foams that were manufactured, but they also are used in the manufacturing of firefighting equipment and clothing. The properties of PFAS chemicals in terms of their water repellency make them ideal for, say, firefighting jackets and pants. They're also very thermally stable, so they're widely used in those industries. They're also used in the food processing industry for coatings on food packaging. And you can see my example here. Picture the wrapper of your favorite fast food burger. Just try to picture, unwrapping that burger and feel the texture of that packaging. It's very waxy and very slippery. It repels fats and oils. It's also used, I like to say in this picture in the back here, for the onion rings that get served at Red Robin. The basket liner is a wrapper with PFAS coatings. Makes them ideal for this application. On a little side note, I just noted today that Burger King has introduced reusable sandwich containers and also reusable food containers. I'm not sure how that's supposed to work, but I think part of it is in the, addressing, recycling and getting some of these products out of the waste cycle. So PFAS are also used extensively in household products like non-stick coatings. We talked about that before, like Teflon, textiles, upholstery, carpet, and leather. We talked a little bit about that previously. Medical products, metal plating, oil production are some applications. Mining, of course, paper and packaging, because they're oil and water repellent. If you've ever received like a water repellent cardboard box, like you could feel that waxy surface, they're used quite extensively there. They're used in photolithography and semiconductors. And of course, because the nature of this chemistry, they're used in textiles as water repellent fabrics, okay? So widely used in many, many industries. Okay. Any questions about the use and applications? Okay, seeing none and hearing none, I will press on. Let's talk a little bit about how PFAS chemicals have wound up in the environment, like how they're released in the environment. So one of the sort of most talked about ways in which PFAS chemicals are released into the environment, you've probably become familiar with this, is you hear it in the context of firefighting foams. So these aqueous film forming foams, the PFAS chemicals, they have ideal properties for the suppression of hydrocarbon fires. And they were also widely used in fire training areas. So places that you've heard about where PFAS is, they find in high concentrations are around airports, because airports do a lot of fire suppression training. So they've released a lot of this chemical, in the drains around airports. And you also hear a lot about them on military bases for the same reason. They're used quite extensively on military bases for fire training. They've also been, accidentally released from storage tanks, rail cars, and during transfer. Other major sources of PFAS in the environment, obviously where they're manufactured and also where they're used extensively. So many industrial sites, like primary manufacturing facilities like textiles and leather processors, paper mills, metal finishers, wire manufacturers, plating facilities, all responsible for leaking or discharging PFAS chemicals into the environment. They wind up in wastewater through off-site disposal, also accidental release, and also stack emissions. Landfills, of course, are a major source. I like to say not all landfills are created equal, and they certainly, landfills in the 30s, the 40s, the 50s, and the 60s were not the same sort of landfills that they engineer these days. So landfills are a major contributor through contaminated industrial waste. So the waste's got to go someplace. Water treatment facilities that dispose of sewage sludge, any mitigation site waste that winds up in a landfill, and also treated consumer goods like furniture, that's been disposed of in landfills, clothing, things that were treated with these chemicals that wind up in landfills are also major sources of contamination. And also wastewater treatment plants through either point source discharge or leakage due to unintended release. So these are primary ways that PFAS chemicals wind up in the environment. Any questions about that? Don't hear any, don't see any. So we'll move on to some treatment technologies for PFAS. Obviously, PFAS winds its way into the water, either drinking water, source waters, surface waters. They've, also been found in spring waters. So, big question, certainly questions that I've been asked is how can PFAS be removed? And it turns out that, the most common filtration technologies are very efficient at removing PFAS to the degree that they're removed to below the detectable level. So these are the technologies that are primarily used: granular activated carbon, of course, ion exchange resins, membrane filtration, and also reverse osmosis. All four of these technologies, which we're very familiar with, are very effective in removing PFAS from water. Now, the issue associated with this is that they can remove PFAS chemicals from the water, but they haven't eliminated them. Okay, as we had said earlier, they're forever chemicals. So if you use granular activated carbon to remove PFAS, you've got PFAS contaminated granular activated carbon, and you've got PFAS contaminated ion exchange resin, and you've got PFAS contaminated RO discharge. So you haven't, you've certainly not eliminated PFAS from the equation. You've just effectively removed it from the water that you might be treating. But these are all very effective technologies for removal. There are factors that can impact the treatment, like what other co-contaminants are being sort of removed simultaneously. Total organic carbon can compete with things like granular activated carbon, natural organic matter, vegetation that might be in surface waters can compete, other minerals and anions. So if you're, in the process, if you're trying to remove PFAS, these are things that you also have to keep in mind as you plan your treatment methods. Okay, any questions about that? Okay, in that case, we'll move on to the last section of the presentation, which has to do with the regulatory environment. So the reason that PFAS chemistry certainly has attracted the attention of regulators is, for a few reasons. First of all, PFAS chemistry, PFAS compounds, they're extremely mobile. Okay, they easily move around, certainly in water, surface water, drinking water. They're very mobile, partly due to their hydrophobic nature. So they're very mobile. They're persistent. We've talked about that before. It's sort of the forever chemical notion. They're very persistent in the environment. They are bioaccumulative, okay, which means that they accumulate in your body. Okay, they are not easily eliminated, and they also do not easily degrade. Okay, so the very fact that these chemicals possess these properties, mobile, persistent, bioaccumulative, and non-degradable, it's one of the reasons why they're getting so much regulatory attention. So let's start with the US EPA. The US EPA has been on this subject for quite some time. They certainly have developed action plans. You can go to the EPA website and look specifically at the PFAS action plan that they've developed. So I know I've talked about this before, but one of the actions that the EPA took was to include certain PFAS chemicals in the unregulated contaminant monitoring process. So they were included in the UCMR 3. They included these 6 PFAS chemicals, some of which you might recognize, others which hopefully you should be able to draw after this presentation. PFAS, PFOS, PFOA, PFNA, then polyfluorohexane sulfonic acid. I expect that you should all be able to draw that. Perfluoroheptanoic acid, and perfluorobutane sulfonic acid. These 6 compounds were all incorporated in the unregulated contaminant monitoring rule by the EPA. They did find these chemicals in public water systems. They didn't find them in a tremendous number of them, but they did find them at very low levels in the sub-part per trillion, in the part per trillion level. So having found them in the UCMR3, they have sort of pressed on from a regulatory perspective. And they came out with this statement: to provide Americans, including the most sensitive populations, with a margin of protection from a lifetime of exposure to PFOA and PFOS from drinking water, the EPA has established a health advisory level at 70 parts per trillion. So this was their sort of reaction to set a health advisory level for just these two compounds, the combination of these two or individually, PFOA and PFOS at 70 parts per trillion. So any questions about that? Okay, I'll move on. So as we're all probably aware, the EPA has established a health advisory level of 70 parts per million, but what they have not done is establish an MCL. The consequence of that is that many states, as you certainly are all aware up in the Northeast, certainly aware that many states are acting in the absence of EPA MCL establishment. This graph here, courtesy of the American Water Works Association, which was just updated September 1st of this year, sort of gives you an overview of some of the states and how they're regulating PFAS and at what levels they're regulating PFAS. And you can certainly look at this resource on your own, but it does kind of give you the impression that PFAS is being regulated at various levels across the states, certainly at different levels. And so I came upon this quote: in large part, the difference between drinking water guidelines reflects the response to scientific uncertainty. So I found that to be an interesting statement, and sort of relative to the fact that the levels that are being established for PFAS are sort of all over the place. So as I said here, PFAS drinking water guidelines are literally all over the map, but primarily due to, at least the research I did, due to scientific uncertainty about PFAS, and we'll talk a little bit about that. So I'm going to focus on these three regulatory agencies: the EPA and its health advisory level of 70 parts per trillion for PFOA and PFOS; New Jersey, which has established MCLs. They started with PFNA at 13 parts per trillion, and they recently added PFOA and PFOS at 14 and 13 parts per trillion. I'm not sure how this 1 part per trillion difference is established between PFOS and PFOA. And because you're up in the Northeast, you may not be aware, but I will tell you that Michigan has just regulated PFAS in public water supplies. They've established MCLs for 6 compounds. I've got 3 of them here. They've established levels, MCLs, for PFOA at 8 parts per trillion, PFOS at 16 parts per trillion, and PFNA at 6 parts per trillion. So this is almost a 10-fold difference between Michigan's level of MCL for PFOA and the EPA Health Advisory of 70. So I started looking into why that was. That was sort of where my research led me, is how is it that these chemicals are being regulated at such different levels, even though the levels are relatively small. We are still talking about parts per trillion here, so very, very low numbers. So let's look a little bit at that. And the thing that I went to and where that sort of research led me to were the current toxicology studies that are associated with PFAS. The development, and I say here this quote, the development of any maximum contaminant level or drinking water guideline should be based on robust science and risk-based criteria. I think that would be, everyone would sort of agree with that. So I started doing a little looking at toxicology studies. Basically, toxicology studies with regard to PFAS, they look at PFAS exposure. So how are people being exposed to PFAS? And then they look to what are the critical health effects that PFAS can have. And having established exposure and critical health effects, they try to establish what they refer to as this derived reference dose, which is associated with the establishment of a maximum contaminant level. So this is kind of the purpose of a toxicology study, to come up with this derived reference dose. So I started doing a little bit of research into this. So what do the toxicology studies look at? First of all, PFAS exposure. So as I had mentioned earlier, as far back as the 1970s, PFAS, they identified that occupationally exposed workers were accumulating PFAS in their bodies. So they started looking at these folks for exposure risks. Also, communities where people were living near manufacturing facilities with high levels of PFAS measured in the drinking water. And if you can recall just the sheer number of industries that are involved in the use of PFAS chemicals, it certainly is not hard to imagine that lots of people have been exposed being close to manufacturing facilities, and also populations exposed to high background levels of PFAS. So all based on sort of the exposure to humans. What was interesting to note about my look into toxicology studies were that most studies were focused on laboratory animals versus human exposure. Some of the critical health effects that they've attempted to establish include liver damage, increased cholesterol, and LDL cholesterol, reproductive and developmental toxicity, immunotoxicity, endocrine disruption, also tumor induction in highly exposed individuals. So they basically tried to establish a link between exposure and these critical health effects in their toxicology studies. What the studies indicated, although they were primarily based on laboratory animal studies, was that PFAS chemicals are rapidly absorbed in the body, they're widely distributed, and they're not biotransformed or metabolized. So they're very difficult to get rid of. They're not transformed and they're not metabolized. And you can refer back to the discussion about the stability of those chemicals, the fact that they're very strongly bonded, they're very hard to break down, and they don't break down easily in the body. Although if they do get eliminated, they're eliminated primarily in urine. So this is sort of the aim of the toxicology studies, to establish this reference dose based on these studies. But again, what I was trying to discern was, why is there such a great variation between like 3 of these regulatory agencies and the levels at which PFAS were being regulated? And as you can see here, there's sort of a wide gap between some of these levels. And so this was the conclusion that I came to in my research. The EPA and the individual states are using very different methodologies for establishing critical health effects. And the consequence of that is that they are getting like wildly different versions of what the reference dose might be. Although I would say that most of them are very, very conservative. But as you can see here, the EPA, when it looked into PFOA in terms of toxicology studies, it used reduced ossification of mouse phalanges and accelerated onset of puberty, while New Jersey used increased relative liver weight in male mice, and Michigan used neurodevelopmental and skeletal effects. So 3 very different types of studies to try and establish an MCL or a reference dose for PFOA. The same holds true for PFOS. The EPA used reduced rat pup weight at birth, while New Jersey used decreased plaque forming cell response, which is an immune function, and Michigan stuck with their neurodevelopmental and skeletal effects. So again, 3 different toxicology health effect outcomes to establish a level for PFAS and MCL. And the consequence of that is that they came up with different levels, wildly different levels. PFNA, the EPA did not establish a health advisory level for that, but New Jersey did, using increased maternal liver weights of mouse mothers at term, and Michigan used decreased body weight and developmental delays in newborn mice. So again, very different toxicology studies to try to establish MCLs. So my assessment of this is that, that the toxicology studies, the science, as I mentioned earlier, it's not yet well developed. There's a lot of uncertainty associated with it. And the consequence of that is that states, particularly, you can see that the states are regulating at very, very low levels, at very conservative levels, are using, much different numbers than, say, the EPA is using. So, so that was sort of my assessment of the toxicology studies and an explanation for why the numbers were so varied. Does anyone have any questions about that at this point?
Where's New York on PFAS testing now?
I'm sorry?
New York State, where are they
Yeah.
now? On
New
PFAS?
York State, they have, they're also proceeding with the establishment of, I could go back to the previous slide, but New York is also establishing levels of PFAS in drinking water. So what I'd like to end with here very quickly is just a quick summary of the analytical methods before we get into some questions. So if you are getting this work done, if you're getting your water, your source water, and your finished product tested, the current analytical method that's dominating is the EPA 537.1 method. So you should make sure that that your laboratory is using that method for the testing. This is a common list of what's included in the EPA 537.1. This is an 18 analyte selection. Some of these chemistries you should now be familiar with. Some of them are a bit more complicated, but these are both long chain, short chain, and Gen X chemicals. One of the laboratories that we work with considerably, I just got an email this morning, they've expanded their list to 46 analytes that can be tested by 537.1. So just make sure that you're using the right method. And the last thing that I'll say about PFAS in terms of the analytical side is that you should be very, very careful with the sampling because as we've seen, PFAS chemicals are very pervasive in the environment. They're on many, many products. They're very easy to transfer from one, from yourself to the sampling. And the result of that is that you could potentially get false positives, which is why it's very important to make sure that you're using the laboratory supplied lab blanks that come with it, but also proper hand washing and anything that you can do to prevent the accidental contamination of your samples to avoid false positives. Very, very important. So that concludes my presentation. We've been over a fairly broad assessment of PFAS chemicals, chemistry, properties, the history, industrial applications, environmental release, treatment, and regulatory environment. And here are some of the references that I used for your information. And that's the end of my presentation. So at this point, I'm open for questions if there are any. So let's see, I've got a question from Tara. It says, several water companies in Northeast Corridor have tested positive for low levels of PFAS, and 2 are closed as a result, and a 3rd company has very low levels and may be faced with ceasing operations, so it doesn't matter if you're below the recommended MCLs. And that is more of a statement than a comment, but that is definitely true. Any
Steve,
other
we
questions or
had-
comments?
Steve, we had one that popped up in the Q&A
Okay.
portion that asks, what does FDA have to say?
Well, the FDA is sort of in the same place as the EPA, which, the EPA hasn't ruled, and the FDA has sort of followed suit. So really nothing from the FDA.
Hey, Steve, it's Tara.
Hey, Tara.
Hi. Hey, I manage a small water company in our town. It only has 30 connections, and the state is now going around and has contacted us to do the PFAS testing. It's going to be on at their cost. They're going to go, they're going to send it out and do everything with it. And I had a long conversation with the gentleman who's sending out the information to me. And one of the issues with that system is that it has 3 sources. It has a well that produces some water for it, and the other water is groundwater and spring water, which goes right into the cistern and is chlorinated automatically. So getting a raw sample of the spring water and the groundwater was going to be incredibly difficult. Is that going to be a problem?
Is that going to be a problem? Like, I'm not sure what you mean by a problem in terms of collecting, or a problem in terms of testing.
Well, it will not be a clean raw sample of the spring source and the groundwater source. I can get a clean sample from the well source, but the other already goes automatically is in the cisterns themselves and is already chlorinated in that cistern.
Well, I think if you are unable to separate the sources and you get a detect of PFAS, the only complication is that you're not quite sure where it's coming from. You're not sure whether it's, coming from a spring or coming from the groundwater. I mean, ultimately they're interested in the water that's being distributed, to the community. So, whether that, what level of PFAS those are detected at.
Okay, good. I'll let you know how it works out. They're sending me the kits shortly.
I mean, have they said, you've got to sample all 3 of those individual sources, or are they saying, just the water that winds up being distributed to the community?
They came back when I explained how the whole system worked, because this person had no idea. We're going to do the well separately because we can, and the other is just going to be a combined.
Sure, right.
Nothing else we can do.
Right. Any other questions?
Said one other one pop up, Steve, in the Q&A. What would a town water supply do to rectify a PFAS problem?
So, there, as I mentioned earlier, there are, some very effective treatments for PFAS, either granular activated charcoal or RO, or some kind of filtration. So, I mean, it just depends on the levels that they find at this point.
Ultimately, I think public water supplies are allowed to use point of use and point of entry filtration devices. if they can't get it out of their system.
So I have another, thank you, Jack. I have another question about are the labs set up to test at the part per trillion level? And in fact, any laboratory that's running 537.1 method, that method is well capable of detecting PFAS in the sub part per trillion, certainly in the single digit part per trillion level. So well below the, any regulated MCLs. So any laboratory that's testing for PFAS using that method would be able to test at that level. Anything else? I see I'm running over my time. So any other questions?
I don't see anything else in the Q&A, Steve.
If not, I'll turn it back over to you, Jillian. Thank you so much for the opportunity. Appreciate speaking with everyone today.
Thank you, Steve. And
Yes.
thank you for the painless chemical lesson.
I do my best.
Yes, thank you so much, Steve. We always appreciate additional information on PFAS because it is always changing, that's for sure. And we look forward to having you back again tomorrow morning.
Yep, I will be there. Although 8 o'clock's a little early for me, I have to say.
I know, I apologize.
Especially without breakfast.
Exactly. So,
Sarah, you were in charge of that. Didn't you get that memo?
I didn't get the memo.
Darn it.
all right, I will see you all back again in the morning.
Thank you,
Bye,
Steve.
Steve.
Thank you.